Somewhere in our galaxy right now, a star is dying so quietly that no telescope will ever record its end. Somewhere else, another star is ripping itself apart in an explosion bright enough to briefly outshine every other star in its galaxy combined. And somewhere else still, a star far more massive than either of them is collapsing straight into a black hole without any explosion at all, vanishing as if it had never existed. Stars do not die in one single way. They die in at least 15 radically different ways, and some of them die twice. Tonight we're going to walk through every single pathway a star can take to its end. And by the time we finish, the night sky will look nothing like it did before. Before we dive into this, if you're enjoying these deep space explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To begin, we have to be honest about what the phrase stellar death even means, because it is one of the most misleading pieces of vocabulary in all of astronomy. A star is not really a thing that lives and then stops living the way an animal does. A star is a process. It is a self-sustaining nuclear reaction held together by its own gravity, radiating light and heat outward until something in that delicate balance finally gives way. When astronomers say a star has died, they usually mean the core has stopped fusing atoms quickly enough to hold itself up against the weight of its own outer layers. The active, fusion-powered star ends, but almost none of its matter actually disappears. Most of it either drifts outward into space, or it gets locked away inside a small, extremely dense remnant that can sit quietly in the darkness for longer than the current age of the universe. So death here is a convenient metaphor. It marks the end of a phase, not the end of matter. And that phase can end in a startling number of ways. 100 years ago, an astronomer might have given you one or two answers. Today, the honest answer is closer to 15 distinct pathways. And even that simplifies things because several overlap. Several are still being argued about, and some involve events nobody has ever directly observed, but that our best physics insists must happen. Stars do not follow a single script. What decides which script a star follows is not one property, but a whole competition between many properties. Mass matters, of course. A star with the mass of our sun cannot die the same way as a star with 30 times that mass, no matter how hard it tries. But mass alone is nowhere near enough to predict a star's fate. What matters just as much is how much of that mass the star actually holds onto by the end of its life. Because stars are constantly bleeding themselves into space through stellar winds. The chemical composition matters, especially the fraction of elements heavier than helium, which astronomers loosely call metallicity. A star rich in heavy elements loses more mass through winds than a nearly pure hydrogen and helium star of the same size, because heavier elements make the outer layers more opaque and easier for radiation to push around. Rotation matters because a fast-spinning core mixes its layers differently and produces very different explosion geometries. Whether the star lives alone or with a companion matters enormously, because a companion can strip layers off, dump layers on, or eventually collide outright. And what the star's core actually looks like at the moment gravity finally wins, that final core structure is the single most important predictor of what remnant will be left behind, if any remnant is left behind at all. All of that means two apparently identical stars, born in the same nebula from the same gas, can meet radically different ends simply because one of them had a companion nearby and one did not. Or because one of them formed in a slightly denser region and held onto more mass. Or because one of them spun faster and mixed its own core more efficiently. Stellar death is not a lookup table. It is the outcome of a long negotiation between gravity, nuclear physics, geometry, and luck. So let us begin at the gentlest end of the spectrum, with the deaths that are so quiet they barely announce themselves at all. The smallest true stars in the universe are the red dwarfs. These are stars with somewhere between about 8% and roughly 60% of the Sun's mass. And they are, by an enormous margin, the most common type of star in the galaxy. Roughly 3 out of every 4 stars in the Milky Way is a red dwarf. They are dim, they are cool, they are red, and they are extraordinarily long-lived. So long-lived, in fact, that talking about how a red dwarf dies is talking about an event that has never actually happened. Not once. Not anywhere in the universe. The universe is only about 13.8 billion years old, and the smallest red dwarfs are expected to keep quietly burning hydrogen for something on the order of 1 trillion years, possibly much longer. So when we describe a red dwarf's death, we are not describing anything astronomers have observed. We are describing what physics tells us will eventually happen, deep in a future so distant that our own sun will have been gone for longer than the universe has currently existed. The reason red dwarfs live so absurdly long comes down to a single word: convection. Inside a star like our sun, the innermost layers where fusion happens are separated from the outer layers by a boundary the fuel does not easily cross. Our sun fuses hydrogen in a small central region, and once that central fuel runs out, the sun has no easy way to reach the vast reservoir of unused hydrogen, sitting just outside the core. Something like 90% of the hydrogen the sun was born with will never touch the fusion reactor. But a small red dwarf is different. A small red dwarf is convective almost all the way through, like a pot of water at a rolling boil. Fresh hydrogen from the outer layers gets continuously mixed down into the core, and helium ash gets carried back out. This means a red dwarf can, in principle, burn nearly every atom of hydrogen it possesses. Where our sun will use only about 10% of its fuel before its core changes, a red dwarf can use almost the entire pantry. It is the most fuel-efficient object in the universe, and because it is so efficient and because its rate of fusion is so slow to begin with, a red dwarf simply keeps shining. And shining. And shining. For hundreds of billions of years. For 1 trillion years. In some cases, for several trillion years. Eventually though, even a red dwarf runs out. Its central helium content grows, its interior structure slowly changes, and it briefly gets a little hotter and bluer before the end. It does not, however, swell into a red giant. Red giants exist because stars like our sun develop a specific inner structure with a helium core and a hydrogen-burning shell just around it. And that shell burning is what produces the runaway swelling of the outer layers. A small red dwarf never develops that structure, because convection has been mixing everything the whole time. There is no clean layered onion for the star to become. When its fuel is finally exhausted, the star simply contracts, cools, and becomes a helium-white dwarf. A dense, quiet ember of nearly pure helium, small enough to fit inside the volume of the Earth, holding roughly the mass the star had before. It then cools for a period of time that is, honestly, meaningless to human intuition, radiating away its stored heat into an ever-darkening cosmos, Notice how quiet this ending is. There is no explosion. There is no shell of glowing gas expanding out into the interstellar medium. There is no bright flash for astronomers on distant worlds to record. The star simply fades. If every red dwarf in the galaxy died today, most of the universe would never even notice. Now, step up in mass. Take a star like our Sun, with roughly 1 solar mass, and follow its trajectory forward. Our Sun has been burning steadily for about 4.6 billion years, and it has enough hydrogen fuel in its core to keep going for roughly another 5 billion years before the story starts to shift. When that shift comes, the core will finally run out of usable hydrogen, and the outward pressure of fusion will begin to falter. Gravity, patient and undefeated, immediately starts pressing the core inward. As the core contracts, it heats up, and that heat ignites hydrogen fusion in a thin shell surrounding the core. This shell burning is far more energetic than the calm central fusion the Sun does now, and the extra energy pours outward and inflates the outer layers of the star to enormous size. Our Sun becomes a red giant. At its peak, the Sun's outer atmosphere will swell out to somewhere near the current orbit of the Earth, possibly farther, and the outer edge will glow a dull red because that vast bloated envelope is spread so thin it cannot maintain a high surface temperature. Mercury will be swallowed. Venus almost certainly. Earth's fate is genuinely still debated, because the Sun will lose so much mass by that point that its gravitational grip on the Earth will loosen and Earth's orbit will drift outward. And there is a real chance our planet escapes being physically engulfed, only to be scorched into a barren rock instead. Meanwhile, deep inside, the core continues to contract and heat until it becomes hot enough to fuse helium into carbon and oxygen. That ignition often happens as a sudden event called the helium flash, and it briefly rearranges the star's inner structure. The helium flash deserves a closer look, because it is one of the strangest hidden events in stellar physics. When helium finally ignites in the core of a low-mass red giant, it does not ignite gently. The core has become degenerate by that point, meaning it is being held up by electron degeneracy pressure rather than by ordinary thermal pressure, and degenerate matter has a peculiar property. Heating it does not cause it to expand. So when helium ignition begins in a degenerate core, the temperature rises, the fusion rate skyrockets, the temperature rises more, and the fusion rate skyrockets more. For a matter of seconds, the core is producing energy at a rate that dwarfs anything else the star has ever done in its life. At the peak of the flash, the core is briefly releasing as much energy as an entire galaxy of ordinary stars. And yet, from the outside, essentially nothing happens. The star does not brighten. The outer layers do not visibly change. The reason is that all of that stupendous energy is absorbed by the surrounding envelope, which lifts the degeneracy of the core, restores normal thermal pressure, and settles the system down into stable helium burning within a few minutes. The most violent event that will happen inside our Sun before its death is essentially invisible from the surface. If aliens on a nearby world were watching the Sun undergo its helium flash, they would see nothing unusual at all. Meanwhile, the deepest core would have just experienced a runaway that briefly exceeded the luminous output of hundreds of billions of stars. For a while, our Sun will burn helium in its core more or less stably, sitting on what astronomers call the horizontal branch, a period lasting perhaps 100 million years, during which the star looks superficially normal from outside, despite the very different physics operating inside. Then that core helium will also run out, and the star will develop an even more complicated shell-burning structure, with helium fusing in one shell and hydrogen fusing in another, wrapped around a growing core of carbon and oxygen. This is the asymptotic giant branch phase, and it is when the star begins to shed itself. The outer layers of an asymptotic giant branch star are only loosely held. Pulsations in the interior, driven by thermal instabilities in those two shells, push the atmosphere upward and outward in slow waves. Radiation pressure grabs those upper layers and pushes further. Dust condenses in the cooling outer atmosphere and gives the radiation even more leverage. The result is a strong stellar wind that peels the star from the outside in. Over hundreds of thousands of years, the star sheds a huge fraction of its total mass this way, sending gas rich in carbon, nitrogen, and other freshly forged elements out into space. This is where a lot of the carbon in your own body ultimately came from. Cooked in the shell of a dying star, just like the sun, and then blown out into the interstellar medium to be recycled into new solar systems. And then, at the very end of the asymptotic giant branch phase, something remarkable happens. The mass loss rate does not just continue at its usual pace, it suddenly accelerates. What had been a strong wind for hundreds of thousands of years becomes, over the final 10 to 20,000 years, a superwind. The star begins dumping mass into space at rates hundreds of times higher than before, peeling off the last of its envelope in a geological blink of an eye. It is as if the star, having patiently exhaled for eons, suddenly gasps out the last of its outer layers all at once. The transition is so rapid that the star briefly becomes surrounded by a thick shroud of freshly ejected material, obscuring itself from view before that material has time to disperse. Eventually, the outer layers are gone entirely, and what remains is the hot, exposed core. A small, incredibly dense sphere of carbon and oxygen that no longer has any fuel it can fuse. This is a carbon-oxygen white dwarf. The gas the star cast off, illuminated for a few tens of thousands of years by the ultraviolet light of the exposed core, glows in delicate colored shells, and this is what astronomers call a planetary nebula. It has nothing whatsoever to do with planets. The name is a historical accident from the 18th century, when the earliest telescope views made these round, glowing shells look vaguely like the disks of the outer planets. And crucially, a planetary nebula is not a supernova. There is no explosion, there is no shockwave, there is no core collapse. A planetary nebula is the slow, luxurious exhalation of a star that has simply run out of its more manageable fuels. And what it leaves behind is not a neutron star or a black hole, but a peaceful white dwarf that will spend the rest of eternity cooling. That white dwarf is a strange object. It is roughly the size of the Earth, but it contains about half the sun's mass, sometimes more, and it is held up against gravity by something called electron degeneracy pressure. This is a purely quantum mechanical form of support that has nothing to do with heat. You could cool a white dwarf all the way down to absolute zero, and it would still resist being crushed further because electrons refuse to occupy the same quantum states as their neighbors. A single teaspoon of white dwarf material would weigh several tons on Earth, and this is why a white dwarf can persist essentially forever. It does not need fuel to exist. It just needs to be left alone. But quietly, over billions of years, something remarkable happens inside a cooling white dwarf. The carbon and oxygen ions, which had been drifting freely as a hot plasma, begin to slow down as the temperature drops. At a certain point, they can no longer move past each other. They lock into place. The interior of the white dwarf crystallizes, starting from the center and working outward, forming what is essentially a lattice of carbon and oxygen nuclei held rigidly in an ordered structure. From the outside, nothing about the star's appearance changes. It continues to glow faintly, radiating its stored heat. But inside, it is slowly becoming, of all things, a diamond. A cosmic diamond the size of a planet, forged not by pressure alone, but by the patient cooling of the Ionic Sea. Astronomers have identified white dwarfs in the galaxy that appear to have already crystallized substantially, and the largest of them contains crystallized carbon on a scale that dwarfs anything humans could ever mine. The universe grows diamonds, one dead star at a time, over intervals of time that make human civilization look like a moment. This crystallization process is not just a curiosity, it sets a clock, because the rate at which a white dwarf cools depends predictably on its mass, its composition, and its crystallization state. Astronomers can look at the coolest, oldest white dwarfs in the galaxy and use them to measure how long ago the first stars in our region of the Milky Way finished their lives. The dimmest white dwarfs in our galactic neighborhood have been cooling for something close to 10 billion years. They are essentially cosmic clocks, ticking down through radiation for the entire age of the galaxy, and they will keep ticking, quieter and dimmer each eon until they become invisible to any telescope we know how to build. They will never fully cool. They will just become fainter than anything can detect. Our nearest example of this endpoint is not far away at all. Sirius, the brightest star in the night sky, is actually a binary system, and its companion, Sirius B, is a white dwarf, the remnant of a star that finished its life long before humanity existed. Sirius B is more massive than what our own sun will eventually leave behind, because its progenitor was a heavier star, but the basic endpoint is the same kind of object. When you look at Sirius on a clear night, you are looking at a preview, in a sense, of the future of every star like the sun. A tiny, dense, slowly cooling ember hidden in the glare of a brighter companion, radiating its stored heat into the dark. There is a variation of this pathway that produces something even smaller and lighter. If a low-mass star has a closed binary companion, that companion can strip away the outer layers of the star before it ever ignites helium in its core. When that happens, the exposed core is not a carbon-oxygen mix. It is a smaller ember of nearly pure helium, essentially the same kind of object that a red dwarf will eventually leave behind after trillions of years. Except this time it appears within the current age of the universe because the companion did the peeling job in a fraction of the time. The stripping usually happens through something called Roche lobe overflow, where the star's expanding envelope crosses an invisible teardrop-shaped gravitational boundary and starts flowing onto the companion star, or through a common envelope phase in which the companion actually spirals inside the outer layers and drags them off from within. Helium-white dwarfs formed this way are relatively common in binary systems and in dense globular clusters where close stellar encounters happen often. They exist because gravity gave the star a friend that would not let it grow old in peace. This is worth pausing on for a moment because it illustrates something that will matter over and over again. Two stars of identical mass identical composition, and identical rotation can produce completely different remnants simply because one of them had a nearby companion and the other did not. A star that would have quietly become a carbon-oxygen white dwarf on its own can instead end its life stripped down to a helium ember, or in some cases can be forced to donate so much of its mass to a companion that its final structure barely resembles what it would have been in isolation. Binary companions do not just influence stellar deaths, in many cases they define them. And since a large fraction of the stars in the galaxy are in binaries, this is not a rare exception. It is closer to the rule. Now push the mass up further, into the range between roughly 7 and about 10 times the mass of our Sun, depending on which model you trust. These are the intermediate mass stars, and they occupy an awkward middle zone in the death diagram. They are too heavy to end as ordinary carbon-oxygen white dwarfs, because their cores get hot enough to ignite carbon fusion, but they are typically not heavy enough to fuse all the way to iron, and undergo the kind of violent core collapse we will get to shortly. They walk a tightrope. What they usually produce, if they walk it successfully, is a different flavor of white dwarf, one made mostly of oxygen and neon with a smaller admixture of magnesium. The process is a wilder version of what a star like the Sun goes through. These stars swell into red giants, and then into what astronomers call super-asymptotic giant branch stars. Their cores contract and heat and ignite carbon fusion, but that carbon burning is unsteady, occurring in thermal pulses and in shells rather than as a calm central fire. The star sheds enormous amounts of mass through stellar winds, even more aggressively than a star like our Sun does during its own asymptotic giant branch phase. If the mass loss is efficient enough, and this is one of the places where stellar models still disagree, the star peels itself down before its core can grow heavy enough to trigger anything more violent. The final result is a hot, exposed core of oxygen and neon, an oxygen neon white dwarf, surrounded briefly by an ejected shell of gas before that shell dissipates into the interstellar medium. The boundary here is genuinely fuzzy, and this matters. If a super asymptotic giant branch star loses just a little less mass than it needed to, or if its core is just a little bit denser than the models predicted, then instead of stopping at a peaceful oxygen neon white dwarf, the core can be pushed past a threshold where its own electrons start being captured onto atomic nuclei, and the pressure supporting the star suddenly evaporates. When that happens, the star does not become a white dwarf at all, it collapses. That collapse is one of the pathways we will get to shortly. What matters here is that whether a star of 8 or 9 solar masses becomes a quiet oxygen neon white dwarf or a collapsing core depends on details we cannot yet measure precisely. The same star, born under slightly different conditions, could go either way. It is the closest thing to a coin flip in stellar physics. Look at what we have already covered, and how much ground we have crossed without a single explosion. Red dwarfs, so patient they have never actually finished dying anywhere in the observable universe. Stars like our Sun that swell into red giants, exhale planetary nebulae, and settle into carbon-oxygen white dwarf retirement. Low-mass stars in binaries whose companions strip them into helium embers before their time. Intermediate mass stars that thread the needle between quiet retirement and violent collapse, and leave behind exotic oxygen neon white dwarfs when they succeed. All 4 of these endings leave remnants. All 4 scatter enriched material into the galaxy, and yet none of them would show up on a survey of bright transient events. They are the invisible majority. Most of the stars that have ever existed will die in one of these ways. If you look up on a clear night, more than half of all the stars currently shining in the universe will one day end in something this quiet. There is a strange and beautiful symmetry to it. The smallest, most common stars die by fading. The stars like ours die by exhaling. Even many of the middleweight stars die by peeling themselves apart in slow motion. Almost every stellar death you have just heard about happens on a timescale so long or so gentle that if you were watching from a nearby world, you might not even notice it was happening within your lifetime. The gas drifts, the temperatures shift. The star quietly disappears from the main sequence and settles into a compact remnant that will outlast almost every other object we can see. Death here really is closer to retirement than catastrophe. But now the mass climbs, and the physics changes character entirely. Somewhere above roughly 10 solar masses, depending on composition and rotation, and how much mass loss has trimmed the star before its final act, the core structure at the end of the star's life becomes too heavy to be supported by electron degeneracy alone. The oxygen and neon and magnesium in the core start capturing electrons and losing their pressure support. Or the core keeps fusing through neon and oxygen and silicon all the way to iron, and iron cannot save it. In either case, the pressure holding the star up disappears, and gravity, which has been waiting since the moment of the star's birth, finally gets to finish what it started. The core falls inward at speeds approaching a quarter of the speed of light. And what happens next is not a quiet fade. It is the loudest single event in the visible universe. That is where we go next. The moment we leave the world of quiet fading behind, the story changes character so completely that it can be hard to believe we are still describing the same kind of object. Everything in the endings we just walked through happened slowly. Layers peeled away over hundreds of thousands of years. Cores contracted gently into white dwarfs and cooled into the darkness. Even the fastest of those pathways played out on timescales longer than every civilization in human history combined. What we are about to describe happens in less than a second. To see why, we have to look at what is going on inside a massive star during the last stages of its life. When a star begins its life on the main sequence, it fuses hydrogen into helium in its core, and it can happily do this for millions or billions of years, depending on its mass. But when the core hydrogen runs out, the star does not simply stop. It contracts, heats up, and finds a new fuel. It begins fusing helium into carbon and oxygen. When helium runs out, if the star is heavy enough, it moves on to carbon, then to neon, then to oxygen, then to silicon. Each fusion stage releases energy, which pushes back against gravity and keeps the star from collapsing. Each stage takes shorter than the last because the fuels get less efficient and the core has to work harder to compensate. A massive star can spend 10 million years burning hydrogen, 1,000,000 years burning helium, 1,000 years burning carbon, a few months burning oxygen, and, at the very end, only a day or two burning silicon. It is worth pausing to picture what the inside of a massive star looks like in those final days. If you could slice a 20 solar mass star open in cross-section during its last week of life, you would see a series of concentric shells nested inside each other like an onion. The outermost layer, still enormous and thin, is mostly hydrogen. Below that sits a shell of helium. Below the helium, a shell of carbon and oxygen. Below that, a shell of oxygen and neon. Below that, a shell of silicon and sulfur, and at the very center, a growing ball of iron and nickel. Each shell is fusing the material at its base into the material of the shell just below it, feeding the layer beneath. The star is essentially 7 or 8 stars stacked inside each other, each one running its own fusion reaction at its own rate, each one contributing to the mass of the layer inside it. And the innermost shell, the silicon shell, is running out of fuel at a rate that is genuinely difficult to comprehend. Silicon burning does not take years or months. It takes a day, maybe 2. In the final hours, the shell is dumping so much iron and nickel down onto the growing core that the core's mass increases visibly, minute by minute. It is a machine running as fast as nuclear physics can allow, and it is running toward a wall. At the end of silicon burning, the core of the star is made of iron and nickel. And this is where the whole system runs into a wall built by nuclear physics itself. Iron is the most tightly bound nucleus in the periodic table. When you fuse lighter elements into iron, you release energy. When you try to fuse iron into anything heavier, you do not release energy. You absorb it. The core, which has been supporting itself for the star's entire life by fusing lighter elements into heavier ones, has now built up an object it cannot burn. The furnace has produced its own extinguisher, and it has produced it right in the middle of itself. For a moment, an iron core can still support the weight of the star above it through electron degeneracy pressure, the same quantum mechanical support that holds up white dwarfs. But there is a limit to how much mass electron degeneracy can hold up. That limit, called the Chandrasekhar mass, is about 1.4 times the mass of our Sun, and once the iron core grows past it, no known force can keep the core standing. Electrons get squeezed onto protons to form neutrons, which removes even the degeneracy pressure that was holding things up. And with astonishing speed, the entire core simply falls in on itself. The infall is nothing like the slow contraction of a red giant. The inner region of the core collapses at roughly a quarter of the speed of light. In a few tenths of a second, an object roughly the size of the Earth compresses to something roughly the size of a city. Densities rise beyond anything found anywhere else in the visible universe outside of a black hole. Temperatures climb into the tens of billions of degrees. Atomic nuclei themselves are crushed and dissolved into a soup of neutrons. And when the compression reaches the density of an atomic nucleus, something finally pushes back. The neutrons refuse to be squeezed any further, and the collapse of the innermost region halts abruptly, in a fraction of a millisecond. But the rest of the star does not know that yet. The outer layers of the core are still falling inward at enormous speed, and when they hit the newly formed neutron-rich sphere at the center, they bounce. A shockwave forms and starts propagating outward through the star, powered by the impact of infalling matter on a stiff, incompressible core. This is the birth of a core collapse supernova. Or at least, this is the moment when the possibility of a core collapse supernova is created. Whether that shock actually escapes the star and produces a visible explosion, or whether it stalls, weakens, and gets swallowed back down, is one of the great unsolved problems of modern astrophysics. Before we get to what happens with that shock, we need to detour briefly, because not every star that undergoes core collapse actually builds a full iron core first. Some stars collapse for a different reason, in what astronomers call an electron capture supernova. Recall the intermediate mass stars we left teetering earlier, the The ones just heavy enough to fuse carbon in their cores, but usually not heavy enough to make it all the way to iron. Some of those stars, sitting right at the upper end of that mass range, build up cores made of oxygen, neon, and magnesium. The core stops fusing before it can reach silicon and iron. In principle, it should simply become an oxygen neon white dwarf, and we described that pathway already. But sometimes a star has just enough remaining fuel around the core, and just enough mass in the core itself, that the core grows heavier while it is sitting there. As it grows, its density climbs. And once the density in the core rises high enough, something new starts happening. The electrons in the core begin being captured by the neon and magnesium nuclei. Every time an electron gets absorbed by a nucleus, it stops contributing to the pressure that was holding the core up. This is a subtle process, but its consequences are catastrophic. The electrons were what kept the core from collapsing. Remove them one at a time, and the pressure drops. The core contracts. The contraction raises the density further. The higher density accelerates the rate of electron capture, which drops the pressure further, which drives more contraction, which triggers more electron capture. In a very short time, this runaway takes an object that was supposed to be a slowly cooling white dwarf and turns it into a collapsing core. The collapse itself is broadly similar to the iron core case. The inner region falls until it reaches nuclear densities, a neutron star is born at the center, and a shock wave propagates outward through the star's remaining envelope. But there are important differences. The star that produces an electron capture supernova has a much thinner shell of stuff outside the core than a fully evolved massive star. There is much less material for the shock to blow apart. The explosion tends to be dimmer and less energetic than what a full iron core collapse can produce. In many cases, the visible display is modest, easy to miss, easy to mistake for something less dramatic. It is one of the reasons astronomers suspect that quite a few core collapse events over the years have been electron capture supernovae misclassified as ordinary, faint supernova. The famous supernova in the Crab Nebula, which was observed by Chinese and Japanese astronomers in the year 1054, is a strong candidate for having been an electron capture supernova. The progenitor star was probably not massive enough to build a full iron core, but it left behind a neutron star, and the surrounding nebula is enriched with just the sort of chemical fingerprint the models predict. If that is right, then the most famous supernova in medieval history was actually one of the gentler flavors of core collapse, a subtle event that just happened to be close enough for humanity to notice. Now come back to the mainline case, where the core is made of iron and the shock wave has just formed. What happens next is where the physics gets genuinely difficult, and where astronomers have been arguing productively for more than half a century. The naive picture is simple. The shock wave forms, propagates outward, and blows the outer layers of the star into space. In real simulations, this does not work. The shock does not have enough energy to blast through the layers of infalling matter above it. Every second, more of the star's outer layers rain down onto the shock front, sapping its energy. The shock slows, it stalls, it sits, stuck, a few hundred kilometers above the newborn neutron star, unable to break through. If nothing else happens, the shock will eventually die entirely, and the whole star will just fall onto the neutron star, quietly, with no visible explosion at all. Something else has to happen, and that something else is neutrinos. The collapse of the core produces neutrinos in staggering numbers. Every time an electron is captured by a proton to make a neutrino is released. Every time a nucleus is torn apart by the intense heat, more neutrinos are released. And as the newborn neutron star settles down and cools from a temperature of hundreds of billions of degrees, it radiates almost all of its remaining thermal energy as still more neutrinos. In total, a core collapse supernova releases about 99% of its energy in the form of neutrinos. Only about 1% goes into the visible light of the explosion, and only about 1% of that 1% goes into the actual kinetic energy of the ejected material. Almost everything else, an amount of energy that dwarfs everything a star like the Sun will emit over its entire 10 billion year lifetime, streams outward as neutrinos in the first few seconds. Neutrinos barely interact with anything. They can travel through a light year of solid lead with only a modest chance of hitting anything at all. But there are so many of them, and the layer of stalled shock and infouling matter is so dense that even a tiny fraction of those neutrinos getting absorbed can dump enough energy behind the stalled shock to revive it. The details are still being worked out. Convection helps, rotation may help, instabilities in the shocked layer help. Something called the standing accretion shock instability, in which the whole shock front slushes back and forth, helps. Whatever the exact recipe, the shock gets a second chance, and if it succeeds, it starts moving outward again. Now, with new energy behind it, the shock finally powers through the rest of the star, tearing outward through layer after layer at thousands of kilometers per second, and eventually, it breaks through the star's surface in a blinding flash. A supernova is born. It is worth pausing here to appreciate what we are actually saying. The visible supernova, the event that can briefly outshine an entire galaxy, is a byproduct. The real energy release happened invisibly, in neutrinos, in the first seconds. What we see with our telescopes is a small leak from a vastly larger explosion behind the curtain of the star's outer layers. And this is where the story takes a remarkable turn, because we have actually caught the neutrinos in the act. On the 23rd of February, 1987, a massive star exploded in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way about 160,000 light-years away. It was the closest supernova to Earth in nearly 400 years. Astronomers began observing it within hours of the first visible light. But something else had happened first. Roughly 3 hours before the light arrived at Earth, 3 underground neutrino detectors, one in Japan, one in the United States, and one in Russia, each independently recorded a brief burst of neutrino events. Kamiokande in Japan caught 11. Irvine, Michigan, Brookhaven in Ohio caught 8. Baksan in the Caucasus Mountains caught 5. 24 events across 3 detectors, arriving within about 13 seconds of each other. 24 events sounds trivial. It is not. The neutrinos passing through those detectors during that 13-second window numbered in the tens of trillions. The detectors caught 24 of them because neutrinos almost never interact with anything, and even a dense water tank the size of a swimming pool will only stop a tiny handful. What matters is that those 24 events arrived before the visible light. The neutrinos, which stream out of the collapsing core almost instantly and travel through the star's outer layers essentially unimpeded, reached us first. The visible explosion had to wait for the shockwave to grind its way through the star's atmosphere, which took hours. The neutrinos took the direct route. When the light finally arrived, we already knew, at least in retrospect, exactly when the core had collapsed. We had time-stamped the moment of a star's death from another galaxy, using particles that pass through solid rock, like it is not even there. That detection remains one of the most important events in the history of observational astronomy. It was direct confirmation that the entire theoretical picture of core collapse, the neutrino burst, the timing, the energetics, was essentially correct. We had, for the first time, seen inside a dying star. What the collapse leaves behind depends on how much mass the star had at the moment of collapse and how the explosion mechanism plays out. If the neutron-rich core that forms is below about 2 to 2.5 solar masses, it can stabilize as a neutron star. A neutron star is one of the most extreme objects in the universe. It is only about 20 kilometers across, roughly the size of a modest city, but it holds more mass than our sun. A single sugar cube of neutron star material would weigh about 1 billion tons on Earth. Its surface gravity is so intense that light itself is bent noticeably as it leaves. Many neutron stars spin at astonishing rates, some hundreds of times per second, and if their magnetic fields are strong enough, and if their spin axes happen to sweep across our line of sight, we see them as pulsars, cosmic lighthouses, ticking with almost perfect regularity. But not all neutron stars are ordinary neutron stars. A small fraction of them, perhaps around 10%, are magnetars, and they deserve their own discussion because they are quite possibly the most magnetically extreme objects that exist anywhere in nature. A typical neutron star is already magnetized to a level that dwarfs anything humans can produce. Its magnetic field is roughly 1 trillion times stronger than the Earth's. A magnetar is another 1,000 times stronger than that. Its field is so intense that within about 1,000 kilometers of one, the fabric of the vacuum itself begins to behave differently, and the electromagnetic environment becomes so distorted that ordinary atoms could not exist in their usual shapes. If a magnetar the size of Manhattan were to appear near the Earth, its magnetic field would wipe every credit card on the planet from roughly the distance of the moon, and disrupt electronics on Earth from farther still. How does a neutron star end up this magnetized? The leading explanation involves the rotation of the collapsing core. If the core is spinning fast enough at the moment it collapses, and if the collapse triggers convection in the newborn neutron star during its first few seconds of life, the combination of rotation and convection can act like a dynamo, amplifying whatever seed magnetic field was already present in the progenitor by factors of thousands or millions in a matter of seconds. The result is a neutron star born with a magnetic field so strong that it dominates almost everything else the star does for the rest of its life. Magnetars flare unpredictably, releasing bursts of gamma rays and X-rays that can be detected across intergalactic distances. Some of the most powerful flares ever recorded from within our galaxy, capable of briefly saturating spacecraft detectors on Earth, have come from magnetars, and they are increasingly being connected to fast radio bursts, mysterious millisecond-long pulses of radio energy that we detect from other galaxies at a rate of thousands per day. At least some of these bursts appear to originate from magnetars in distant galaxies, and possibly all of them do. The graveyard of massive stars, in other words, includes some genuinely exotic residents, and we are only now starting to understand how the collapse mechanism ends up producing them. There is another feature of the collapse worth mentioning because it explains something you can see with a telescope. When a neutron star is born, it is not usually born gently. the collapse is often asymmetric. One side of the core collapses slightly faster than the other. Neutrinos stream out preferentially in one direction rather than uniformly. The shock revival happens more strongly on one side than the other. And when the smoke clears, the newborn neutron star is not sitting still where the collapse happened. It has been kicked. The kick can be modest, a few tens of kilometers per second. It can be enormous, up to 1,000 kilometers per second or more. This is fast enough that a neutron star born in the middle of a galaxy can, over a few 100 million years, travel far enough to escape the galaxy entirely and drift out into intergalactic space forever. Astronomers can actually measure these kicks. Pulsars observed in supernova remnants are often found moving through the remnant at high velocity, sometimes near the outer edge, sometimes already outside it. Some pulsars are moving so fast that their motion across the sky can be tracked from year to year with sensitive instruments, and the direction of the kick tends to correlate with the axis of the pulsar's rotation, hinting at the geometry of the underlying collapse. Every high-velocity neutron star in the galaxy is a fossil record of the asymmetry of the collapse that made it, and there are a lot of them. Astronomers estimate that the Milky Way is currently home to 100 million or more neutron stars, many of them born with kicks large enough to have carried them far from their birthplaces. When you look up at the galaxy, you're looking at a sky that is quietly threaded with the runaway shrapnel of ancient explosions. If the collapse produces a compact object more massive than a neutron star can support, roughly 2 to 3 solar masses depending on the equation of state of ultra-dense nuclear matter, no known force can hold it up. Neutron degeneracy pressure fails just as electron degeneracy pressure failed. The object continues collapsing, and it becomes a black hole. This can happen through fallback, where a neutron star initially forms, but then more infalling matter piles onto it and pushes it past the limit. Or it can happen more directly in a way we will return to shortly. And this brings us to a critical clarification. When you look at pictures of supernova remnants in different parts of the sky, they look wildly different from one another. Some have hydrogen in their spectra. Some have almost no hydrogen but plenty of helium. Some have neither hydrogen nor helium. Some show a smooth structure. Some are chaotic and asymmetric. Astronomers use these observed features to classify supernovae into types with names like Type 2, Type 2b, Type 1b, and Type 1c. It is easy to look at that list and assume that each type represents a completely different way that a star dies. But underneath these different spectra, the core physics is largely the same. Something has collapsed. The engine is a stalled shock revived by neutrinos, and the outcome is a neutron star or a black hole. What changes between the classifications is not really the death itself. It is what was still wrapped around the star at the moment it exploded. Consider a massive star that lives out its life alone, holds onto most of its hydrogen envelope, and then undergoes core collapse. When the shock breaks through the surface, the light we see is dominated by that hydrogen envelope being blown apart. The spectrum shows strong hydrogen lines. This is a Type 2 supernova, and it is what most people picture when they hear the word supernova. Now take a nearly identical star, but this time give it either much stronger stellar winds, perhaps because it has a higher fraction of heavy elements to make its outer layers easier to push around, or give it a close binary companion that has been slowly siphoning mass off of it for a long time. By the time this star reaches core collapse, most or all of its hydrogen envelope has been stripped away. The core inside is the same, the engine is the same, The neutrinos still power the shock, but now, when the shock breaks through the surface, there is very little hydrogen out there to blow apart. If some hydrogen remains but not much, we see a Type 2b supernova, which starts out looking like a Type 2, but transitions to something more helium-dominated as the outer thin layer of hydrogen thins out. If all the hydrogen is gone but helium remains, we see a Type 1b. If both the hydrogen and the helium have been peeled away, exposing the deeper carbon and oxygen layers, we see a Type 1c. These are stripped envelope core collapse supernovae, and grouping them together is not a matter of laziness. It is a recognition that the mechanism inside is the same. What differs is the biography of the star. Did it live alone? Did it have a companion? How much material had already been stripped off before the final act? The audience sees a different show depending on which curtains were still hanging, but backstage, the same drama is playing out. This matters enormously, because it means the observed diversity of supernova spectra tells us more about binary star evolution and stellar winds than it does about the fundamental physics of core collapse. Most massive stars, we now think, live with companions at some point in their lives, and companions strip material off with brutal efficiency. If most massive stars end their lives partially or fully stripped, it explains why the observed rate of stripped envelope supernovae is as high as it is. It is not that these deaths are exotic. It is that the ordinary life of a massive star involves companionship, and companionship is a mass thief. Now we come to the most disquieting pathway in this whole part of the story. Because so far, everything we have described ends in an explosion, whether bright and hydrogen-rich or dimmer and stripped down. But some massive stars, and possibly quite a few of them, undergo core collapse and produce almost no visible explosion at all. Their outer layers do not get blown into space. Their shock never successfully breaks out. And the star, instead of going out in the most violent event in the visible universe, simply and quietly disappears from the sky. These are the failed supernovae, and they are one of the strangest recent discoveries in stellar astrophysics. The setup is like an ordinary core collapse. A massive star runs through its fusion stages, builds an iron core, and the core collapses to nuclear density. A shockwave forms, neutrinos stream out, the stalled shock waits, hoping the neutrinos will revive it. And here, in some cases, they do not. The shock is not revived. It stalls and stays stalled, and the outer layers of the star, which were already falling inward, just keep falling. Everything above the core rains down onto the newborn compact object, one shell at a time. The neutron star that formed initially gets crushed by the infalling matter and turns into a black hole. And the star, which was once one of the brightest objects in its neighborhood, just fades. From the outside, if you were watching, you might see the star dim slightly, or brighten briefly as some outer layers get a little heated by the accretion, and then over some months or years, you would see it disappear. There would be no dramatic supernova, just a star that used to be there, and then was not. For a long time, this was purely a theoretical prediction. But over the last decade or so, astronomers have actually caught a candidate. A star in a nearby galaxy called NGC 6946. A red supergiant with about 25 times the mass of our Sun was being monitored as part of a systematic search. In the year 2012, it brightened slightly, flickered, and then simply disappeared. Subsequent observations with the Hubble Space Telescope and other instruments confirmed that the star that had been there was no longer there. There had been no supernova. There had just been a fading, and then silence. The current best interpretation is that this is exactly what a failed supernova looks like. The star's core collapsed. No shock revival succeeded. The whole thing fell into the black hole that formed at the center, and the galaxy became one massive star, quieter, without any of the cosmic drama that a successful supernova would have provided. The word failed here refers specifically to the explosion, not to the formation of a compact remnant. In a failed supernova, the star still dies. A black hole still forms. The core still collapses to something extreme. The failure is only that the outer layers did not get blown away, and that failure has serious consequences for what we see and what we do not see. If a significant fraction of the most massive stars die this way, and current estimates suggest it might be somewhere between 10 and 30% of them, then a real chunk of stellar death in the universe happens entirely off the record, with no bright flash to mark it. There's a strange symmetry to this that mirrors what we saw earlier. Down at the low mass end, red dwarfs die by fading quietly. Up at the very high mass end, some of the most massive stars in the universe also die by fading quietly. The middle is where the fireworks are. It is not the biggest stars that produce the brightest explosions. It is often the ones just above the threshold for core collapse, or the ones that had companions to strip them, or the ones that spun fast enough to produce asymmetric shock revival. The largest stars sometimes have such massive cores that gravity simply wins outright, and the show that should have been the loudest in the sky becomes the quietest. If you find that counterintuitive, you are in good company. For most of the 20th century, astronomers assumed that every massive star produced a supernova. It was only when detailed simulations kept failing to produce successful explosions in the highest mass models that people started taking failed supernovae seriously. Now the evidence is mounting that a real fraction of massive stars end in silence, and it is reshaping our understanding of where black holes come from. Not every stellar mass black hole in the galaxy was born in a bright cataclysm. Some of them, perhaps many of them, were born in a quiet vanishing act that nobody would have noticed at all if we had not been watching carefully. So the mainline core collapse story is more varied than it first appears. Electron capture events at the low end, gentle and dim. Ordinary iron core collapses in the middle, powered by neutrinos and revealed as Type II supernovae. Stripped envelope collapses higher up, showing Type 1b or Type 1c spectra, because a companion or a wind stole the outer layers before the end. And then, at the top of the mass range for this kind of death, failed supernovae, in which the whole star simply falls into the newborn black hole and vanishes. But we are still not at the most extreme end of the story, because there are stars so massive and so violent in their final years that even these pathways do not describe them. There are stars that spin fast enough and hold onto enough mass that when their cores finally collapse, they do not just make a neutron star or a quiet black hole. They make a black hole surrounded by an accretion disk, and out of that disk shoot jets of matter moving at nearly the speed of light. They produce the most energetic single events humans have ever recorded. And beyond those, there are stars whose deaths are triggered not by iron and gravity, but by the sudden creation of matter out of pure energy, a physics that has no analogue anywhere else in stellar evolution. Some of those stars destroy themselves so completely that no remnant remains at all. That is where the story goes next. There is a certain kind of star that ordinary core collapse physics simply cannot account for. When astronomers first start detecting the most powerful stellar explosions in the universe, the ones bright enough to briefly outshine every other star in their home galaxy combined, they realized that the neutrino-driven mechanism we just walked through was not enough on its own. It could produce a bright, respectable supernova. It could not produce what they were seeing. Something else was going on inside the most massive, most violent, most rapidly rotating stars at the moment of their deaths. Something that borrowed physics from black holes, from magnetic fields, and from geometries no ordinary supernova ever explores. That something is what astronomers call a hypernova, and it is our starting point in this next stretch of the journey. A hypernova begins the same way an ordinary core collapse supernova begins. A massive star, far more massive than the ones we have been discussing, runs through its fusion stages, builds a heavy core, and collapses. In this case, though, the star is spinning quickly, and the core inherits that spin. When the core collapses, the same conservation of angular momentum that turns a spinning ice skater into a blur when she pulls in her arms turns the collapsing core into an object rotating hundreds of times a second. And it does not just make a neutron star. If the star was massive enough, it makes a black hole. But this black hole is not sitting quietly at the center. It is surrounded by matter that has too much angular momentum to fall straight in. Instead of plunging into the black hole, that matter piles up into a thick, hot, extremely dense disk that spirals inward slowly, releasing enormous amounts of gravitational energy as it does. This is a collapser. The name simply means a collapsing star that has produced a rotating black hole surrounded by an accretion disk. And what happens next is remarkable. The disk is so hot, so dense, and so magnetically active that it launches jets. Two narrow, focused streams of matter, one from each pole of the newly formed black hole, punch outward through the collapsing star at nearly the speed of light. They drill through the outer layers of the star from the inside out, breaking through the surface in a matter of seconds. And when they finally escape, they carry so much energy in such a tightly focused beam that if the jet happens to be pointed at us, we see one of the brightest single events in the observable universe, a long-duration gamma-ray burst. Long-duration gamma-ray bursts have been detected from across the observable universe. Some of them from galaxies whose light has been traveling toward us for more than 12 billion years, are so distant that they are among the earliest bright objects in the visible sky. They are quite literally the death cries of stars that lived and died when the universe was only a fraction of its current age, and they are almost certainly, at least the long-duration ones, the jets from collapses breaking out of dying massive stars. The rest of the star does not sit still while this happens. Some of the collapse's energy also drives an ordinary supernova-like explosion, blowing the outer layers of the star into space. So a hypernova, seen from the right angle and observed patiently over the days and weeks after the initial gamma-ray flash, often shows an underlying supernova as well. The spectrum of these supernovae looks like the spectrum of a Type 1c stripped envelope core collapse event, because these massive rotating stars have almost always shed their hydrogen and helium envelopes long before the end. But the ejecta are moving faster, the energies are higher, and the total kinetic energy of the explosion is roughly 10 times what an ordinary supernova produces. Something extra has happened. Something the ordinary neutrino-driven mechanism cannot account for on its own. The connection between long-duration gamma-ray bursts and hypernovae is now solidly established. When bursts are detected in nearby galaxies, follow-up observations often reveal a bright supernova at the same location, appearing in the days that follow. The two are almost always found together when we can look closely enough. That does not mean every hypernova produces a detectable gamma-ray burst, because the jets are narrowly focused and only visible when they happen to point at us. But when a hypernova's jets do point at us, they light up detectors on Earth-orbiting satellites within seconds, and the burst is often followed hours or days later by the visible glow of the associated supernova. It is worth being honest about a piece of vocabulary here. The word hypernova gets used loosely in popular writing, and even astronomers use it in slightly different ways depending on the context. There is no crisp, universally agreed upon boundary where an ordinary Type 1c supernova ends and a hypernova begins. The word is more of a description of extreme cases than a precise category. Sometimes it means an unusually energetic core collapse event. Sometimes it specifically means one associated with a long-duration gamma-ray burst. Sometimes it just means any collapse that involves jet formation. The physics is real and important, but the label is a bit fuzzy at the edges. What matters is the underlying picture. The most massive, most rapidly rotating stars can, at the moment of collapse, form a black hole plus disk plus jets combination that adds a whole layer of physics beyond what a simpler core collapse involves. And the compact object left behind is a black hole essentially by construction. The rapid rotation and the huge mass of the collapsing core almost guarantee that the newborn compact object is above the mass limit for a neutron star. There is no gentle way this ends. Whatever the star was, it becomes a black hole with a violent birth story wrapped around it. Before we move on, there is a third way for the most massive stars to produce extraordinarily bright deaths. And it deserves its own discussion because it does not involve gravity in the way a hypernova does, nor pair production in the way we are about to discuss. It involves a compact object as the engine of the explosion, driving light out of the ejector for months at a time. These are the magnetar-powered superluminous supernovae, and they are one of the most active areas of stellar death research today. Here is the setup. A very massive, rapidly rotating star undergoes ordinary core collapse. The core does not form a black hole, instead it forms a magnetar. But this is not just any magnetar, it is a magnetar spinning at the absolute limit of what a neutron star can physically sustain, close to 1,000 times per second, with a magnetic field strong enough to be measured in the trillions of times the Earth's. This newborn object contains an enormous reservoir of rotational energy, and because its magnetic field is so intense, it dumps that energy into its surroundings at a prodigious rate, spinning down over months or years as it does. The energy has to go somewhere. It flows outward into the expanding shell of supernova ejector that the collapse threw off, and that ejector, being heated continuously from within by the spinning down magnetar, glows for far longer and far brighter than an ordinary supernova. An ordinary core collapse supernova is powered by the radioactive decay of freshly synthesized nickel, and its light curve fades over weeks to months as the nickel decays away. A magnetar-powered supernova is powered by the magnetar itself, and its light curve can stay bright for 6 months, a year, sometimes longer, releasing far more total energy than any ordinary supernova. At their peaks, these events can outshine an ordinary supernova by a factor of 10 or 100, briefly becoming the brightest single objects in their entire galaxies. Some of the most luminous supernovae ever recorded, events so bright that they can be seen from cosmological distances even without the aid of jets pointed at us, are best explained by this mechanism. The star itself is dead. Its ordinary supernova has already happened, but its remnant is now acting as a central engine, pumping light into the expanding ejector for months on end, extending what would have been a modest fade into a spectacular, prolonged public display of dying. This pathway matters because it explains events that neither ordinary neutrino-driven supernovae nor collapsor jets can account for on their own. It also demonstrates something remarkable about stellar remnants. Even at the moment of a compact object's birth, it can shape the visible death of the star that produced it. The star and its remnant are not sequential objects. In this case, they are entangled in a single ongoing event that unfolds over a much longer timescale than the collapse itself. Now, step up further. Because as violent as hypernovae are, they are still fundamentally driven by gravity winning over pressure and by the geometry of a spinning disk. There is another way for the most massive stars in the universe to die, and this one is not driven by gravity at all. It is driven by pure energy, by the fabric of physics itself, by the fact that under sufficiently extreme conditions, radiation stops behaving like radiation and starts turning into matter. Welcome to pair-instability. Inside a massive, hot stellar core, most of the pressure that holds the star up against gravity does not come from the motion of atoms or from electron degeneracy. It comes from radiation. Photons of extremely high energy bounce around inside the core, pushing outward on everything they encounter, and that outward push is what keeps the whole enormous structure from collapsing. As long as the photons stay as photons, the pressure holds, and the star is stable. But if the core gets hot enough, something new starts happening. The individual photons are carrying so much energy that they can spontaneously convert into pairs of particles, an electron and a positron. This is not exotic. This is a consequence of Einstein's mass-energy equivalence, written down more than a century ago. Sufficiently energetic photons can turn into pairs of matter and antimatter particles. Under most conditions, this is not important. Under the conditions inside the core of a very massive star just before it dies, it becomes decisive. Here is why it is decisive. When a photon turns into an electron-positron pair, it stops contributing to radiation pressure. The pair might annihilate a moment later and become photons again, but for the fraction of time it exists as matter, its contribution to the pressure is gone. In a hot enough core, this pair production starts happening on such a large scale that it takes a real bite out of the total radiation pressure. And when the radiation pressure drops, the core is no longer able to support the weight of the star above it. The core contracts. The contraction raises the temperature. The higher temperature accelerates the rate of pair production, which drops the pressure further, which drives more contraction, which produces more pairs, which drops the pressure further still. This is a runaway, and the same pattern that we saw in the electron capture case is playing out here, but for entirely different reasons. Now, the runaway does something that no other kind of stellar collapse does. As the core contracts and heats, it eventually reaches temperatures where the oxygen in the core suddenly ignites in explosive nuclear burning. Not the calm, controlled oxygen burning that a normal massive star does before core collapse, but a runaway thermonuclear explosion all at once, throughout the entire oxygen-rich region of the star. Fusion energy dumps into the core faster than the star can absorb it. What happens next depends sensitively on how much mass the star has at that moment. If the star's core mass at the moment of the pair instability event is in a certain range, roughly between about 40 and about 60 times the mass of our Sun, the explosion is violent enough to eject a large portion of the outer envelope, but not violent enough to completely disrupt the star. The core survives. The star, having thrown off a huge amount of mass in a single terrifying pulse, contracts back down and continues its evolution. Except now, with less mass and a different internal structure, it may reach conditions where the pair instability triggers again. Another pulse, another huge shell of material ejected, another temporary reprieve. This can happen multiple times over years, decades, or centuries, with each pulse throwing off tens of solar masses of gas. This is pulsational pair instability, and it produces one of the most exotic pieces of observational astronomy. Repeated shells of ejected material, sometimes visible as glowing rings around the star, and eventually the star's real death, when either its structure finally changes enough to avoid triggering another pulse, or when a final collapse produces an ordinary core collapse or hypernova event. The star, in a sense, dies in installments. It has near-death experiences, ejects material, survives, and then does it again. And when a subsequent shell of ejector collides with an earlier one, the collision itself can produce a brilliant flash of light, an interaction-powered display that can look to distant observers like a whole extra supernova. There is at least one famous case in the literature, an object called SN 2006 Groi, which was so bright and so long-lasting that ordinary supernova physics could not explain it. One leading interpretation is that it was a pulsational pair instability event, in which shells of ejected material collided with one another, releasing energy over months and months, and producing one of the brightest supernova-like events ever recorded. If that interpretation is correct, then what we saw was not one death, but a whole sequence of near-deaths, each one throwing off part of the star, and the accumulated collisions of the debris giving off enormous amounts of light for a long time afterward. But there is another regime, and this is the truly extreme one. If the star's core mass is even higher, in the rough range of about 60 to 130 times the mass of the Sun, the pair instability does not just cause a partial ejection. The runaway thermonuclear ignition of oxygen deposits so much energy into the star, so quickly and with such totality that the entire star is unbound. Every layer, from the deepest core to the outermost atmosphere, is blown apart. The gravitational binding energy of the star is exceeded, and nothing remains. This is a full pair instability supernova, and it is the most complete destruction of a star that the universe knows how to produce. There is no neutron star. There is no black hole. There is no compact remnant of any kind. The star simply ceases to exist as a bound object. Everything it was becomes an expanding cloud of gas and freshly forged elements, drifting outward into space. Nothing at all is left behind to mark where the star used to be. If that sounds difficult to believe, it should. It goes against everything the earlier discussion was building. In an iron core collapse or a hypernova, the collapse of the core is what triggers the whole event, and the core is what becomes the remnant. In a pair instability supernova, the collapse never happens. Because before gravity can win, the explosive oxygen burning has already blown the whole thing apart. There's nothing left for gravity to collapse. This is worth pausing to appreciate. When you go through the mass ranges we have covered so far, you find that the more massive a star is, the more violent and complete its death tends to be, up to a point. Red dwarfs die by fading. Sun-like stars die by shedding their outer layers and leaving small remnants. Massive stars die by core collapse and leave neutron stars or black holes. Even more massive stars at the extreme top end sometimes die by collapsing directly into black holes with no explosion at all, as we saw with failed supernovae. But then, at a slightly different corner of the parameter space, the very most massive stars can die in an event so violent that no remnant survives. The escalation is not monotonic. The universe does not simply keep adding more force at each step. It changes the underlying physics as the mass climbs, and at certain thresholds, the results go in different directions, and it does not stop there. If the star's core mass is even higher still, above about 130 solar masses, the pair instability actually stops mattering. Because at those temperatures, the photons carry enough energy to interact with atomic nuclei in a whole new way, breaking them apart and swallowing more energy than pair production alone releases. In these truly enormous stars, the pair instability blowup does not have time to complete before the whole core collapses directly into a black hole. A very massive star, above roughly 130 solar masses at the moment of core collapse, likely collapses right through the pair instability regime and into a black hole, with little to show for it observationally. Above that mass range, we are back to a form of direct collapse, essentially another flavor of failed supernova. But for stars so massive that they were probably never even common in the first place. Now, when do these pair instability events actually happen in the universe? The core mass required is enormous, and modern massive stars generally cannot reach it because they lose too much mass through stellar winds before the end. A star born today, in a galaxy like the Milky Way with a modern chemical composition, has a stellar wind strong enough to peel off tens of solar masses over its lifetime. The heavy elements in its outer atmosphere make radiation pressure very efficient at pushing material off, and by the time the star reaches the end of its life, its core, while still massive, is not massive enough to sit in the pair instability regime. But the early universe was different. The very first generations of stars formed from gas that contained essentially only hydrogen and helium, with none of the heavier elements that were manufactured by later generations. Without those heavy elements in their outer atmospheres, the first stars had extremely weak stellar winds. They held onto almost all of their mass throughout their lives. And they were also larger to begin with, because the initial gas was easier to compress into massive clumps in the low metallicity conditions of the early universe. Those two facts together mean that stars of 100, 150, even 200 solar masses may have been genuinely common in the first few 100 million years after the Big Bang. And if they were common, and if they held onto their mass through the end, then pair instability supernovae may have been a common ending for the most massive early stars. Some of the heavy element enrichment we see in the oldest, most metal-poor stars today may be the chemical fingerprint of those ancient pair instability blowups which threw enormous amounts of freshly forged material into the young universe, with no compact remnant to trap any of it. In the modern universe, pair-instability supernovae are expected to be rare, requiring unusual conditions to occur. But they may still happen occasionally. In low metallicity dwarf galaxies where wind stripping is inefficient, or in dense stellar clusters where two massive stars can merge and end up with a combined mass in the pair-instability range. Astronomers have identified a small number of candidates over the past 2 decades. Unusually bright and long-lasting supernovae, with spectra and light curves that are hard to explain any other way. Not every candidate is confirmed. It is a young area of observational research, and interpretations shift as more data comes in. But the theoretical case is compelling, and pair-instability supernovae almost certainly happen, at least occasionally, even now. Now come back to the middle case, the pulsational pair-instability regime, because there is something specifically interesting there about the black holes it leaves behind. If a very massive star undergoes a series of pulses and finally collapses, it can produce a black hole. But the pulses will have thrown off so much of the star's outer envelope that the final remnant mass is limited. This means that even for stars starting with truly enormous masses, the resulting black holes come out with masses bounded from above by the pulsations. Above a certain mass, and until the direct collapse regime kicks in at very high core masses, the pair-instability pulsations effectively prevent black holes from being made in a certain intermediate mass range. This creates something called the pair-instability black hole mass gap, a range of roughly 60 to about 130 solar masses, in which no black holes are expected to be born from ordinary stellar collapse. Because any star that would have made a black hole in that range instead either lost too much mass to the pulsations or was disrupted entirely by a full pair-instability event. This gap is more than a theoretical curiosity. When gravitational wave detectors on Earth started catching the ripples in space-time produced by merging black holes far out in the universe, one of the striking findings was how the observed masses of the merging black holes are distributed. Most of the observed black holes fit comfortably below the pair-instability mass gap, or at least near its lower edge, exactly as the theory predicts. When a merger appears to involve a black hole whose mass is inside the forbidden gap, astronomers immediately have to explain how it got there, because a single star should not have produced it. The usual answer is that the black hole is itself the product of an earlier merger, a black hole made of black holes, so to speak, formed in dense stellar clusters where compact objects can pair up multiple times over the age of the universe. The pair-instability gap is one of the ways stellar death physics leaves a fingerprint on the black hole population billions of years after the fact. And now, step back and look at what we have said. Some stars collapse into ordinary neutron stars. Others collapse straight into black holes. Others still form black holes surrounded by accretion disks and jets, powering the most violent flashes in the universe. Some never reach the collapse stage because pair instability blows them apart in pulses, delaying their real death by centuries. And some never reach it at all because pair instability destroys them completely, leaving nothing behind but an expanding cloud of freshly minted elements. 5 very different endings, all of them variations on what the largest and most extreme stars do at the end of their lives. All of them driven by physics that has no analog anywhere else in nature. There is a piece of intuition that this deserves to overturn, and it deserves to be stated plainly. If you ask most people to guess which stars produce the brightest deaths in the universe, they would probably guess the biggest ones. And that intuition is wrong. Some of the biggest stars in the universe collapse directly into black holes with almost no visible display, dying quietly through failed supernovae, as we saw earlier. Some of them produce hypernovae, yes, and those are extremely bright. But the very biggest stars, the ones that would have been the most impressive of all, are the ones whose deaths are least likely to be seen at all, either because pair-instability tore them apart with no remnant, or because their sheer mass forced a direct collapse with no explosion. The middle range, and only the middle range, produces the fireworks. The extremes produce quiet vanishings or complete disappearances. Visible brightness is not a measure of how important a stellar death was. It is a measure of how much of the death happened above the surface of the star rather than beneath it. And in the largest cases, almost none of the death happens where we can see it. There's one last thing worth noting before we move on. Everything we have covered up to this point has been about how a star dies through some form of instability in its own core or in its own radiation. Gravity wins, or pair production wins, or the geometry of a spinning disk wins, or the shell of an ejected pulse collides with the next shell and lights up. But all of these mechanisms happen because of what is going on inside the star itself. There is a completely different family of stellar deaths in which the star is not really killed by its own internal physics at all. It is killed by something outside it, either a companion star, or a compact object, or an accretion process that turns a peaceful stellar remnant into a runaway thermonuclear bomb, or a black hole large enough to shred any star that wanders too close. Those deaths are strange in a different way. They involve stars that had already left the fusion-powered phase behind, or stars whose destruction was triggered by another object's proximity, or stars that never intended to explode, but were pushed into it by conditions they did not create. Some of them are among the most important events in cosmology, because they let astronomers measure the size of the universe itself. Others are the deaths that create the heaviest elements in existence, including the gold in wedding rings and the platinum in catalytic converters. And some of them turn a star inside out in an event so rare that only a handful of examples have ever been confirmed anywhere in the sky. That is where the story goes next. Everything we have covered so far has ultimately been about what a star does to itself. Now we have to turn to a different family of deaths, ones in which the star is not really killed by its own internal physics at all. The killer is fusion, yes, but fusion in the wrong place, at the wrong time, in an object that had already retired from the fusion business. Or the killer is another star entirely, colliding with, merging with, or feeding upon its partner. Or the killer is a black hole that a star wandered too close to. These are deaths of a different flavor, and one of them is arguably the single most important explosion in modern cosmology. Start with the classical thermonuclear supernova, the Type 1a. Almost everything we have said so far in this documentary has assumed that a white dwarf, once formed, is a peaceful, permanent end state. Cool, contract, cool some more, cool for the rest of eternity. That is what happens to most white dwarfs. Most of them will still be sitting quietly in the sky in 1 trillion years, doing nothing except radiating away the last of their stored heat into an ever colder universe. But some white dwarfs never get to reach that fate. They live near companions, and when a white dwarf lives near a companion, It can be pushed slowly or quickly past a threshold it was never supposed to cross. The threshold is the same Chandrasekhar mass we met earlier in the collapsing iron cores of massive stars. The 1.4 solar mass limit above which electron degeneracy pressure can no longer support the object. A white dwarf sitting at less than this mass is stable. A white dwarf pushed above this mass cannot be stable. And when it crosses over, something new begins. As the star contracts under its own weight, the temperature at its center rises. The carbon and oxygen inside, which have been sitting cold and inert for billions of years, are suddenly hot enough to fuse. And this is where the geometry of the situation matters, because a white dwarf is a degenerate object. In a normal star, when you heat the fuel, the star expands, cools, and the fusion self-regulates. In a degenerate white dwarf, heating the fuel does not cause the object to expand. The pressure does not depend on the temperature, so the temperature rises, the fusion rate skyrockets, the temperature rises more, the fusion rate skyrockets more, and within a few seconds, the entire white dwarf is undergoing runaway carbon and oxygen burning at every point simultaneously. There is no time for the star to expand. There is no time for the star to cool. There is no shell burning, no gradual outward propagation of the front. The entire object, top to bottom, ignites almost as one. And when it ignites, it releases so much nuclear energy in so little time that it exceeds the gravitational binding energy of the entire star. The white dwarf, which had been sitting quietly for hundreds of millions or billions of years, is completely destroyed in a matter of seconds. Nothing survives. There is no remnant. The exploded material, moving at thousands of kilometers per second, races outward, carrying with it a huge amount of freshly synthesized iron and nickel. The event that observers on distant worlds see is a supernova, one that can briefly outshine an entire galaxy of 100 billion stars. This is a Type 1a supernova, and its importance to modern astronomy is difficult to overstate. Because these explosions happen when a white dwarf reaches essentially the same critical mass every time, their peak brightness is roughly the same every time. Astronomers can compare how bright a Type 1a supernova appears in a distant galaxy to how bright it should be. And from that difference, calculate the galaxy's distance. This is how the accelerating expansion of the universe was discovered in the late 1990s. The distant Type 1a supernovae were dimmer than they should have been, meaning the galaxies containing them were farther away than expected, meaning the universe's expansion had been speeding up rather than slowing down. Dark energy, whatever it turns out to be, was inferred from the light of these exploding white dwarfs. Cosmology as we know it stands on this pathway of stellar death, but there is a genuine puzzle about exactly how the white dwarf reaches the critical mass. There are two main scenarios, and honestly, the debate about which one dominates has been going on for decades, and is not fully settled. In the first scenario, the single degenerate pathway, the white dwarf has a normal companion star, and it steals mass from that companion over millions of years. The companion is bloated, or evolved, or in a close orbit, and material flows from it onto the white dwarf's surface. Slowly, gram by gram, the white dwarf grows heavier, until it approaches the critical mass and ignites. In the second scenario, the double degenerate pathway, there is no ordinary companion. Instead, there are two white dwarfs in a close orbit. Gravitational radiation slowly drains energy from the orbit over hundreds of millions of years, drawing the two white dwarfs together and eventually they either collide directly or the heavier one tears the lighter one apart and swallows its material. Either way, the combined system exceeds the Chandrasekhar mass, and one runaway thermonuclear explosion later, both white dwarfs are gone. For a long time, astronomers assumed the single degenerate pathway was the main channel, but the evidence has become more complicated. Searches for the surviving companion of a nearby Type 1a supernova have often turned up nothing, when the single degenerate model predicted a bright companion should still be there. Rates of white dwarf mergers, calculated from surveys of the galaxy, look high enough to account for a substantial fraction of Type 1a events on their own. The honest answer at this point is that both pathways probably contribute, and the fraction of each may vary depending on the age and composition of the host galaxy. What matters for our purposes is the physics of the death itself. Whichever pathway pushes the white dwarf past the threshold, the outcome is the same: complete thermonuclear disruption, no remnant, and a burst of light that can be seen from cosmological distances. Now, there is a variation on this theme that produces something completely different, and it is one of the strangest recent additions to the catalogue of stellar deaths. Sometimes a white dwarf begins the runaway thermonuclear burning, but the burning is incomplete. It does not consume the whole star. It ejects a portion of the mass, produces a much dimmer explosion than a normal Type 1a, and leaves behind a bound remnant, a white dwarf that survived its own detonation. Astronomers call these Type 1ax supernovae, and the surviving remnants have picked up the informal nickname zombie stars. The physics is delicate. In a normal Type 1a event, the deflagration and detonation fronts propagate through the star and process essentially all the carbon and oxygen into heavier elements, releasing enough energy to unbind the whole object. In a Type 1ax event, either the burning starts in the wrong place, or it fails to transition from deflagration to detonation, or the white dwarf ignites slightly below the critical mass through some non-standard channel. The burning fizzles out partway through, and while the outer layers get blown off, the inner regions remain gravitationally bound. What is left behind is an odd object. A white dwarf that has been partially processed by its own aborted explosion, sitting there like a wounded survivor of an event that should have destroyed it entirely. These events are dimmer than normal Type 1a supernovae, sometimes by factors of 10 or more, and they are correspondingly harder to detect at large distances. But surveys have turned up a growing number of them, and in a few cases astronomers have been able to identify what appears to be the surviving remnant star, moving fast through space, ejected on a trajectory that is consistent with the event that nearly destroyed it. This is important for a couple of reasons. It shows us that thermonuclear disruption of a white dwarf is not always all or nothing. It reminds us that Type 1a supernovae are not perfectly standard candles, since a variable population of failed explosions can contaminate the sample if not handled carefully. And it opens up the possibility of studying up close an object that lived through its own death. Now leave the world of thermonuclear explosions and turn to a different class of death entirely, the kind that involves stars physically running into each other or merging with each other. Space is mostly empty, and the direct collision of two ordinary stars in the general field of a galaxy is genuinely rare. But in dense stellar clusters, or in the closed binary systems that hold a huge fraction of the massive stars in the galaxy, mergers happen regularly. The most common form is a slow merger driven by orbital decay. Two stars in a closed binary can be pulled together over time by tidal effects, by stellar winds, by mass transfer, and by the interactions of a common envelope in which one star's outer layers surround the other. Eventually, the two stars come into contact and the outer layers begin to mix. If the two are similar in kind, if both are ordinary main sequence stars, for example, the merger typically produces a single, more massive star, altered by the process but still recognizably a star. It may spin quickly, it may show unusual chemical composition on its surface because deep interior material has been dredged up and mixed outward. It may briefly be brighter or bluer than either progenitor, and there is often a transient outburst associated with the final coalescence, a temporary flare of light called a luminous red nova, as the merger releases gravitational binding energy and shocks the surrounding gas. A merger does not always destroy matter. Usually most of the mass of both stars ends up in the merged product. Some fraction gets thrown off, sometimes into a disk around the merger remnant, sometimes into space entirely. But the point is that when two stars merge, one modified survivor typically emerges. It is a death in the sense that the two original stars, as separate objects, no longer exist. It is not a death in the sense of matter being destroyed, or a compact remnant necessarily forming. The merger is a transformation more than an ending. There is a lovely piece of observational evidence for how common these mergers are, and it comes from looking at old star clusters. In every ancient globular cluster in the galaxy, in fact, in every dense stellar environment where astronomers can measure the ages of individual stars, there is a population of objects that simply should not exist. They are bright, blue, and hot, exactly like young stars, sitting in a cluster where every other star is old and red. Astronomers call them blue stragglers, and they have been a puzzle for over half a century. A star cluster is a single stellar family, born together, aging together. There should be no genuinely young stars in a 15 billion year old cluster, and yet there they are. The current best explanation is that blue stragglers are merger products. Somewhere in the cluster's long history, two ordinary old stars in a close binary system spiraled together and merged into a single, heavier star. The merged product looks young because it is more massive than either progenitor and burns hotter and bluer, exactly like a young star should. It is essentially a rejuvenated corpse, a star that lived through its partner's death by absorbing it. Every dense cluster has these ghosts of ancient mergers walking around inside it, and their existence is one of the cleanest pieces of evidence that stellar mergers are not exotic. They happen all the time. Mergers between different types of objects lead to different outcomes. A red giant merging with a smaller companion can produce a star with an unusual internal structure. A star merging with a white dwarf can, in some circumstances, produce an object that then behaves like a Type 1a supernova, or that becomes a strange chemically peculiar star with a helium envelope. And mergers involving compact objects, neutron stars, and black holes produce some of the most extreme events in the universe, which we will return to when we discuss the second deaths of stellar remnants. Now, the other category of external destruction, the kind driven by black holes. When a star gets close enough to a black hole, the difference in gravitational pull between the near side of the star and the far side of the star can be greater than the star's own self-gravity. When that happens, the star is not just pulled toward the black hole, it is pulled apart. Its near side accelerates toward the black hole faster than its far side. The star is stretched out along the direction toward the black hole and compressed perpendicular to it. Eventually, the star's self-gravity loses the battle, and the star is disrupted, torn into a long stream of gas that trails behind its original orbit. This is a tidal disruption event, and it happens most commonly when a star wanders too close to a supermassive black hole at the center of a galaxy. It can also happen with stellar mass black holes in some circumstances, but the classic case is a star straying into the vicinity of one of the giant black holes that sit at the hearts of most galaxies. When a tidal disruption event happens, about half of the disrupted star's material eventually falls onto the black hole, forming a temporary accretion disk that shines brightly across a huge range of wavelengths for months or even years. The other half of the star's material is flung outward on hyperbolic orbits, escaping the black hole entirely and drifting into intergalactic space. There is a specific distance from any black hole called the tidal radius, inside which the tidal forces exceed the star's own binding energy and the star gets torn apart. Outside that distance, the star survives the encounter intact. Right at the boundary, something interesting happens. If a star's orbit brings it just barely inside the tidal radius, only the outer layers of the star are stripped, and the dense core survives. Now the surviving core is on an elongated orbit that will bring it back to the tidal radius again and again and again once per orbit. Each pass strips a little more of the star. Each pass produces a small flare. And what astronomers see from the outside is a black hole that is periodically flaring over and over again on a regular schedule as the same wounded star returns to be nibbled at again. These are repeating partial tidal disruptions, and they were only recognized as a distinct class of event in the last few years. Some of the black holes producing them have been caught in the act of slowly eating the same star, one meal at a time, over years or decades. The star is dying by inches. It will eventually run out of material and be destroyed entirely, or its orbit will decay far enough inside the tidal radius that a single close pass finishes it in one full disruption. Either way, it's a slow and unusual death, and it is one of the strangest new pieces of the stellar death puzzle. It is worth being clear about what a tidal disruption event actually looks like from far away. Astronomers do not see a star being visibly torn apart. What they see is a bright flare of light coming from the center of a galaxy that was previously quiet. The flare appears suddenly, brightens over weeks, and then fades over months or years as the fresh material from the disrupted star processes through the accretion disk and gets swallowed. From the outside, it looks a bit like a galactic nucleus briefly waking up and then going back to sleep. Only detailed analysis of the light curve and the spectrum reveals that the fuel for this flare was a specific star that got too close. And here is something worth emphasizing, because it is often misrepresented. A black hole does not suck stars in from arbitrary distances. Nothing about a black hole is more gravitationally powerful than any other object of the same mass at the same distance, whether it is a black hole, a neutron star, or a spread out cloud of gas. What makes black holes special is that they can concentrate mass into an incredibly small region, so you can get very close to that mass before hitting a surface. That closeness is what makes tidal disruption possible. But a star has to actually get close, either by having its orbit perturbed by another passing object, or by drifting inward over time through some process, or by being on a highly elongated orbit that brings it near the black hole periodically. Most stars in most galaxies will never come anywhere near their central black hole for their entire lives. Tidal disruption is not the fate of most stars. It is the fate of the unlucky ones whose orbits happen to bring them too close. Now we have covered the 15 major pathways that were promised at the start of this journey. We have walked through the quiet endings, the ordinary core collapses, the extreme deaths of the most massive stars, the thermonuclear disruptions, and the deaths caused by external objects. And it is worth pausing for a moment to note what a huge range of physics we have crossed. We have talked about electron degeneracy pressure, convection, radiation pressure, and shell burning. We have talked about neutrinos, standing shocks, and shock revival. We have talked about pair production, thermonuclear runaways, and tidal forces. We have talked about mergers, jets, and disks. All of these mechanisms are doing the same thing at some level, which is negotiating between gravity, pressure, nuclear physics, rotation, and geometry to determine what happens to a star at the end. But the outcomes are wildly different depending on which of those factors dominates, and it is worth taking a moment to appreciate what remains behind. Depending on which pathway a star follows, the universe ends up with a helium white dwarf, or a carbon-oxygen white dwarf, or an oxygen-neon white dwarf, or a neutron star, or a magnetar, or a stellar mass black hole, or nothing at all. Different chemical fingerprints, different densities, different fates for the future. The graveyard of the galaxy is not filled with a single type of headstone. It is filled with an enormous variety of remnants, each one marking a specific kind of death and a specific set of conditions that led to it. But there is one more layer to this story, and it is important enough to include, even briefly, because everything we have described so far has been the death of a fusion-powered star, the moment when a star stops being an active nuclear engine and either fades away or explodes or collapses. But the remnants that get left behind are not always at the end of their own stories. Some of them have their own deaths ahead of them, later, sometimes billions of years later. And when a stellar remnant dies, it is not really the death of a star. It is the death of what a star left behind. These are second deaths. And they are worth touching on before we close, because they are what the future of the universe is largely made of. Two white dwarfs orbiting each other in a close binary will gradually spiral together, drawn inward by the tiny amount of energy that gravitational radiation carries away from the orbit. Over hundreds of millions or billions of years, the orbit shrinks. Eventually, the two white dwarfs merge. The outcome depends on the total mass of the pair. If the total is below the Chandrasekhar mass, they may simply produce a single, more massive white dwarf, or a stranger object that briefly ignites carbon burning and then settles into something new. If the total is above the Chandrasekhar mass, the merger can produce a Type 1 alike thermonuclear explosion in the way we described earlier. This is one of the double degenerate channels for those events. Either way, two remnants that have been quietly cooling for billions of years become, in an instant, either one heavier remnant or nothing at all. Two neutron stars orbiting each other in a close binary have an even more extreme fate. Neutron stars are so small and so dense that their orbits shrink much faster once they get close, and the final moments of the inspiral produce enormous amounts of gravitational radiation. In the year 2017, human beings detected exactly this event. An object called GW1 70817 for the first time. Ground-based gravitational wave detectors caught the ripples in space-time as two neutron stars spiraled together and merged. Telescopes all over the world followed up within hours and identified the visible glow from the collision, an event called a kilonova in a nearby galaxy. The moments of coalescence are worth trying to picture, because they are unlike anything else in the universe. In the final second before merger, the two neutron stars are orbiting each other hundreds of times per second, each one moving at a substantial fraction of the speed of light. The gravitational waves streaming out of the system are so intense that the amplitude of space-time distortion, if you could stand at a safe distance and watch, would be as loud a gravitational signal as anything short of a black hole merger. When the two stars finally touch, what happens next depends sensitively on their combined mass. If the total mass is well above the maximum a neutron star can support, the merger collapses almost immediately into a black hole, in what astronomers call a prompt collapse. There is barely time for anything else to happen before the horizon closes over the wreckage. But if the total mass is closer to the neutron star maximum, the merger can briefly produce something exotic: a hypermassive neutron star, an object heavier than a normal neutron star should be able to support, but held up temporarily by its own rapid rotation. This hypermassive remnant might survive for milliseconds. It might survive for seconds. It might, in some cases, survive for much longer before its rotation slows enough that it can no longer support its own weight, and it too collapses into a black hole. Whether the 2017 event went through a prompt collapse or a hypermassive phase is still being debated. It is one of the questions that the next generation of gravitational wave detectors is being built to answer. A kilonova is not really the death of an ordinary fusion-powered star. It is the merger of two remnants that already died a long time ago. But it is a real, dramatic event. And it does something extraordinary. When two neutron stars merge, the ejected material is extremely neutron-rich, and the conditions in the ejector are just right for a process called rapid neutron capture, in which atomic nuclei quickly absorb many neutrons in a row before they have time to decay. This is the process that builds the heaviest elements in the universe: gold, platinum, iodine, uranium, and many others. The kilonova detected in 2017 produced spectral signatures consistent with the creation of a substantial amount of gold and platinum in a single event. The gold in wedding rings and the platinum in catalytic converters ultimately came from stars that died long ago and left behind remnants that later merged in exactly this kind of event. Neutron star mergers are one of the main forges of the heavy elements, and they are second deaths in the deeper sense. There are other pathways too. A neutron star that is accreting mass from a companion can, in principle, be pushed past the maximum mass a neutron star can support, and then it collapses into a black hole. This is sometimes called accretion-induced collapse. The neutron star, which had been sitting at just under the limit for a long time, finally gets pushed over, and there is nothing left to hold it up. It becomes a stellar mass black hole in an event that is, from the outside, relatively subtle. Some X-ray brightening as the accretion continues, and then a quieter phase as the newly formed black hole settles down. Similarly, a white dwarf that is being pushed toward the Chandrasekhar mass can sometimes, instead of exploding thermonuclearly, undergo accretion-induced collapse into a neutron star. Whether a white dwarf goes bang or goes crunch under accretion depends on the composition, the density, and the rate of accretion. The universe reserves the option to do either. Compact remnants can also merge with or be swallowed by black holes. A neutron star spiraling into a stellar mass black hole produces a distinctive kind of gravitational wave event, and depending on the mass ratio, it can either be swallowed whole with only a brief tidal disruption, or produce a burst of ejecta and a fainter kilonova-like transient. Black holes merging with black holes produce the loudest gravitational wave events we can detect. These are not the original deaths of stars. They are the deaths of the remnants that stars left behind. But they are real events, and they contribute in real ways to the chemical and dynamical evolution of the universe. The point of walking through these second deaths is not to expand the list of stellar death pathways to some larger number. It is to make clear that a stellar remnant is not necessarily a permanent object. The universe has ways of destroying, transforming, or absorbing even the compact remnants of long-dead stars, and those events can happen billions of years after the star itself first ended. A white dwarf you might have imagined cooling forever might, in 100 million years, merge with another white dwarf and produce a thermonuclear explosion. A neutron star you might have imagined pulsing quietly for eternity might, over 1 billion years, be pushed by accretion into becoming a black hole. And two neutron stars that have been orbiting each other since the early universe might, right now, be within 1 million years of merging and producing enough gold to fill an ocean. Death, for a star, is not necessarily an ending. It is a transition into a new form that may itself have transitions ahead of it. And the whole system is a great cycle of matter. A star forms out of a cloud of gas and dust. It fuses hydrogen for millions or billions of years. It exhausts its fuel and ends in one of the pathways we have walked through, quietly as a white dwarf, or explosively as a supernova, or invisibly as a failed collapse, or completely as a pair-instability blow-up. What it throws off in its death becomes part of the interstellar medium, mixing with the gas that already fills the galaxy. And that enriched gas, richer in heavy elements than it was before, eventually collapses under gravity into new stars and new planetary systems. Some of those new stars are richer in metals than their parents, allowing rocky planets to form. Some of those rocky planets, in certain narrow ranges of conditions, become homes for life. The atoms in your body were forged inside stars that lived and died before the sun was born. The oxygen you were breathing came from stellar winds. The carbon in your cells came from asymptotic giant branch envelopes. The iron in your blood came from supernova ejecta. The gold, if you happen to be wearing any, came from a neutron star merger somewhere in the distant past, well before the Earth existed. Stellar death is not a series of catastrophic endings. It is the mechanism by which the universe recycles itself and slowly, over cosmic time, produces the raw materials for planets, chemistry, and life. The graveyard of stars is also the nursery of new stars. Every death feeds the next generation of birth. And the enormous variety of pathways we have walked through, from the trillion-year fade of a red dwarf, to the vanishing act of a failed supernova, to the thermonuclear disruption of a white dwarf, to the merger of two neutron stars, is not a catalogue of unrelated tragedies. It is a portrait of the different ways matter can transition from one form to another, under the endless negotiation between gravity and everything that tries to hold it back. Somewhere in our galaxy, right now, A red dwarf is patiently burning through hydrogen it will not exhaust for 1 trillion years. Somewhere else, a star like the Sun is beginning to swell into a red giant. Somewhere else, a massive star is running through the last stages of its life at breathtaking speed, only weeks from a core collapse it does not yet know is coming. Somewhere else, 2 white dwarfs are quietly spiraling toward each other, and somewhere else, 2 neutron stars are within a heartbeat of forging the next batch of gold. All of it is happening at once. All of it is happening all the time. And all of it, taken together, is how the universe of stars sustains itself. Generation after generation, death after death, in the enormous, patient, generative cycle that gave rise to everything, including us. Good night. And when you look up next, remember, not one of those points of light is truly permanent. Every one of them, in its own way, is on its way to becoming something else.